Okay, so recall that our greedy algorithm, it for each job, it first computed its score Si, which was the weight Wi divided by the length Li. It sorted the jobs in this order, in the order of this decreasing, right, or non-increasing scores, and it outputs this sorted order as the optimal schedule. And we are trying to understand why this algorithm is actually correct. Okay, so a proof of this will use the exchange trick, right? The exchange trick that we talked about earlier. And we'll do, we have a few assumptions before this. So the assumption one is that all the scores, right? All the scores are different. Okay. So this will just help us simplify the proof a bit, but it's not really essential to correctness of the algorithm. Okay, it will just help us keep the proof a bit simple. And the second one is that we'll just assume that the jobs are numbered in order of decreasing scores. Okay. So what does that mean is that the job which has number 1 is the job which has the highest score. Okay, the job which has index job number n is the job which has the least score. Okay, so we're just assuming this is, of course, this is completely fine to just, does not, we're not losing out on any generality. We're just renaming the jobs such that the job 1, we'll call job 1 as the job which has the highest score, and we'll just, and so on, right? Job n is the job which has the lowest score. So what this implies is that our greedy schedule, right? What is our greedy schedule? It is simply first schedule job 1 because it has the highest score, then you schedule job 2 which has the next highest score, schedule job 3 which has the next highest score, and so on. Finally, you schedule job n which has the lowest score. Okay. So it just simplifies us to represent this greedy schedule, right? So let's call this greedy, maybe give this a name sigma, and we need to show that, right? Sigma is an optimal solution, right? The ordering sigma is, it gives you the least weighted completion time. That's what we'd like to argue. Okay, so now this proof will work by contradiction. It uses this exchange trick, but we will prove it by contradiction. Okay, so what is a contradiction? So let's suppose that sigma is not optimal. Okay, so let's suppose there is some other optimal schedule, sigma star. Okay, so proof is by contradiction. Okay, suppose there exists an optimal schedule sigma star, right? Okay, so, and such that I'll just write this as the cost of sigma star. Okay, cost of sigma star. What is the cost? The cost is simply the weighted completion time. Okay, so there is some other scheduling. Okay, there's some other scheduling which you're calling sigma star, such that its weighted completion time is less than the weighted completion time of our greedy solution, right? this sigma is our greedy solution here, and we are saying that there is some other ordering of the n jobs which has a lower weighted completion time. Okay. Okay. So if this happens, if there is something like this, so let's look at sigma star more carefully. Okay, let's look at this ordering more carefully. Since sigma star is different from the greedy ordering, there have to exist successive jobs in sigma star such that a job, the first job has a lower score than its succeeding job. Okay, so what we're saying is sigma star will have to be something like this. It will have some jobs here, some jobs, and at some point it will have a job I, and then it will have the next job will be job J. Okay, and then it will have some other jobs again. But we are just zooming in on these two jobs, and we are saying that it has to be that um, I is greater than J. Okay, what we are basically saying is that the score of I, right? Score of I is less than score of J. Okay, that's how we have numbered the jobs, right? If I is greater than J, we have said that that means that the score of J is less than the score of, sorry, we have said that if yeah, if J is less than I, then we have said that the score of J is greater than the score of I. Okay, and if sigma star is something like this, we're saying if sigma star is not the greedy solution, if it is not sigma, then there have to be two consecutive jobs of this form. Okay, why is that true? Well, this won't be true for only one ordering. There's only one particular ordering for which this will never happen. Okay, and when that never happens, what is going to be the case is that whenever we have something like this, I and J, we have two successive jobs, we will have that SI will be greater than SJ. Okay, and that only happens for the greedy ordering, right? When we sort them in, when we order the jobs in decreasing scores, right? Only when we order the jobs in decreasing scores, we'll always have SI will be greater than SJ for any two consecutive jobs, right? Okay, so only for the greedy ordering, this particular um, situation, you cannot find such jobs IJ, but for any other job, also for the optimal job, this sigma star that we have considered here, we will be able to find two consecutive jobs I and J such that SI is less than SJ. Okay, so, right. So since SI is less than SJ, what we are basically saying is that the weight of I divided by the length of I is less than the weight of J divided by the length of J, right? That's what we are saying in this case. Okay, right. So maybe we'll keep this, right? This is this inequality is a star inequality, which will be useful for us. Okay, so now what we are going to do in this exchange. So in some sense, we know that the greedy algorithm would not have something like this, right? It would first, if job J has a greater score, it would first schedule job J and then job I. Okay, so let's just exchange these two jobs and see what we get. Okay, so what we say is consider the schedule, let's give it some name, sigma star new, let's say, which is got by swapping jobs I and j, by swapping jobs I and j in schedule sigma, right? Sigma star, sorry. So we take sigma star, we keep this unchanged, we keep this unchanged, we keep this unchanged, we don't change them, but we just swap these two jobs. Okay, so our sigma star new will have the same jobs as in sigma till this point here, right? Till this point it has the same jobs, then it has job j, and then it has job I, and then again all these jobs are the same as in sigma star. Okay, so we have just swapped these two jobs to get a new schedule which we are calling sigma star new. Okay, right, so specify here keeping all other jobs unchanged. All the other jobs, their orderings are not changed. Okay, now consider the cost of this new scheduling. Okay, so let's consider, in particular, let's consider the cost of sigma star minus the cost of this sigma star new. Okay, so what is it? It's the weighted completion time of sigma star minus the weighted completion time of sigma star new. What is the weighted completion time of sigma star? Well, it's the weighted completion time of this plus the wi, whatever this weight of the ith job times its completion time, right? Plus the weight, plus we'll have a similar factor for this, and the weighted completion time due to these. Okay, now we observe that since sigma star new has this and this as the same, their contribution to the weighted completion time is going to be same. It's not going to change, right? So when I consider this difference, the contribution from these two will simply cancel out because they are exactly the same. Okay, the contribution due to these two jobs, well, they will change, so we have to consider that. But we notice that the completion time at this point is the same as this, right? Do we see that? Because these jobs were the same, so this time is exactly the same as this time, and now we are just swapping jobs I and j, so the final time where this jobs I and j finish here is going to be the same as the final time that this jobs I and j finish in this schedule, right? That doesn't change. So what does that imply? So since this time is the same as this time, the weighted completion time due to these terms will be the same as the weighted completion time due to these terms, right? They will depend on the weights and the length and weights and this time here, right? And this time is the same as this time here. So those factors also cancel out in this when I subtract. So what really remains is just the contribution of these terms, right? The contribution of these terms to the weighted completion time. So, right. So let's say this time here is some time t, right? This time um, before at which job I starts. So this time here will also be t, right? The time at which this job j starts. Okay, so now this difference is going to be what is the contribution of these two terms is it's the weight wi, right, times the completion time of I, which is simply t plus the length of job I, right? That's when job I will complete in this schedule, right? And job, the term for job j is the weight of job j plus t plus the length of job I plus the length of job j. That would be, this would be the completion time of job j in this schedule sigma star. Okay, so that would be the term for this, and what remains in this would simply be minus, so the contribution of these two terms to the weighted completion time of sigma star nu is simply weighted, the weight of j times the completion time of j. What is the completion time of j in the schedule? It's simply t plus the length of the job j, right? So that is simply t plus the length of the job j plus the contribution of this term, which is simply the weight of I times t plus the time at which this job completes. The job I completes is Lj plus Li. Okay. This is what that will remain in this expression, right? Everything else we have said will cancel out. Okay. So there are only these two terms that remain. Okay. So I'll let you simplify this, and what basically remains is Li Wj, right, minus Lj Wi. Okay. Everything else will cancel out. And this turns out to be greater than 0. This term turns out to be greater than 0. Okay. Why is that? Well, it's simply coming back to this star expression, right? Wilj is less than Wjli, right? Wilj is less than Wjli. So this entire expression is greater than 0. Okay, so are we done? So what we are basically saying is that this is positive. That is, cost of our sigma star is greater than the cost of sigma star nu, right? So what have we done? Sigma star was an optimal solution, and we have found, just by swapping two jobs in the optimal solution, we have found another solution, right? Another scheduling, which has an even lower cost than the optimal. Okay, which is of course a contradiction, right? So what does that mean? What we assumed was false. What did we assume? We assumed that sigma star was something which was different from our greedy solution sigma, right? So that cannot be the case, which implies that our greedy solution sigma has to be the optimal solution. Okay. So this is another example where this exchange trick is helping us prove the optimality of the greedy solution, right? We considered we assumed that the greedy was not optimal, and in some other optimal solution, we found a way of just switching two parts, right? Exchanging two parts of an optimal solution, right, to find an even better solution than the optimal. Okay, and that is the contradiction that proves optimality.